Today, I'm going to show you several examples of how to use position nodes in your shader. Let's go. Alright, so let's talk about position. Here we are in Unity's shader graph, and I have two nodes here that both bring position data into our scene. First, we're going to talk about this one. Position data is an X, a Y, and a Z value representing location. There are various elements that we can get position data for. First, if we plug our position node into the vertex portion of our master stack, we're getting position data for each of the vertices of our model. So our model is made up of triangles, and a triangle has 3 vertices or points. And so this position, if I use it in the vertex portion of my master stack, is bringing in the positions of those vertices. If I plug my position node into the fragment portion of my master stack, I'm actually getting the positions of each individual pixel of the model. Position data is just numbers that represent location, but we can visualize the numbers as color if we plug the position data into the base color and or the emissive portion of our master stack. So you can see here now in my preview, I have my position data represented as color with X represented as red, with Y represented as green, and with blue representing the Z data. And you can see that it's going from black to colored as the data goes from -1 on this side of the sphere over to positive for X. And also on the y-axis here, I'm going from negative down here at the bottom of the sphere to positive up here at the top of the sphere. So if we place our sphere into a test scene, you can see that the colors are on my sphere here as well. This manipulator shows you a convenient way of visualizing it. You can see that the x-axis is represented as red on my manipulator, and the y-axis is represented as green, and the z-axis as represented as blue. And we can see those same colors on my sphere because right now I'm mapping this position data as color onto my object through the shader. If I move my object around, you can see that the colors on the sphere are staying the same. They're not changing because these colors are relative to the pivot point of the sphere. And as my sphere moves, the pivot point is moving with it, so the colors are moving with the sphere. Why is that? If we switch back to our shader here, you can see that my position is currently set to object space, and that means it's relative to the object itself. So wherever the object goes in the scene, the position data is going to go with it. The pivot point of my sphere is right in the center, and so the colors or the position data are relative to that pivot point. Now if I rotate my sphere, you can see that the colors are rotating with the sphere, and that's because the pivot point is rotating, and so the data is rotating with it. That's what happens when our data is in object space. It's relative to the position and rotation of the sphere. But let's take a look if we switch our position data from object space to absolute world space, and we save our shader. Now, as we move our sphere around, you can see that as the sphere moves away from the center, the colors are actually changing because the data is relative to the center of my world rather than the center of my sphere. So you can see that I have to, in order to see those colors, I have to keep them relatively close to the center of the world. And as I move it away from the world, the colors become quite different. If I rotate my object with the data in world space, the data stays intact because it's relative to the world. It doesn't care about my object's rotation. So I'm rotating my sphere all around, but my colors are staying exactly the same. And that's because they represent the position in the world and not the position of the object. So they're not tied to the object's rotation anymore. All right, so that's really interesting. We have some position data for our object that we can represent either in object space or in world space. But what can we do with that? Let's take a look at a couple of examples of ways that we can use this position data. So in this first example, we're going to take a look at, we're creating a bit of a stylized look. There are a lot of artists that like to create models where they darken the model at the bottom of the model, and then as we go up the model and higher, we get brighter toward the top. This works really nicely on characters, especially like stylized characters. And we do this darkening so that your focus is kind of on the head or the face of the character, and you pay less attention to maybe the feet and the body. But as we go up the character, we get brighter and brighter. So let's take a look at how we can do that using object space position. So here I have my position node and it's set to object space. Then I'm using my swizzle node to just isolate the Y axis or the Y of the position data. And this basically turns my position data into a really nice gradient that goes from dark at the bottom and bright at the top. And remember, it's relative to wherever the pivot point is. And in my case, the pivot point is in the center of the sphere. So right now I've got positive data going from the center up, and I've got negative data going from the center of the sphere down toward the bottom. In order to shift these values around a little bit, I need to multiply, which is going to expand or contract the range. So I'm going to multiply it by 0.6, which contracts the range a little bit. And then I'm going to add 0.5, which is going to shift the range down. So here you can see my pivot point is in the center, but because I've added 0.5, I've shifted it toward the bottom. And now I'm going to adjust the data with power to kind of increase the contrast. I'm going to raise it to a power of 2. Just so we can take a look at what's happening, I want to sort of interactively adjust this data. If I set it to adding 0, I'm just going to close this power node for now because it's going to do some wonky stuff. You can see if I add 0, I've got my pivot in the middle. But as I increase this value, I'm pushing the pivot point down toward the bottom of the sphere. And I can just set this to like whatever I want it to be. In my case, I'm just going to set it to 0.5. And then as I said, I'm going to raise it to a power of 2. Now let's plug this data into our color and our emissive and take a look at the results in our scene again. You can see how that looks on our model here. Now you can see that I have a model that is dark at the bottom and brighter at the top. So if I had a nice character here, I would get kind of a simulation of a little bit of ambient occlusion, like really broad ambient occlusion, because the character would be dark at the bottom and bright at the top. All right, so that's one way of using position data in my shader to add a gradient to my character so that it's dark at the bottom and bright at the top. Okay, let's take a look at another example. And in this example, what we want to do is we're placing rocks or trees in our environment, and we want those rocks or trees or whatever these instance objects are that we're placing in our environment, we want them to be slightly different colors depending on their location. So let's take a look at this example now. And before we take a look at this example, I want to show you a different kind of position, and that's object position. Let's go back up here to the top. You can see I've got two nodes here. I've got the position node, and I've got the object node with position coming out of it. This could be kind of confusing because I have position here and I can put it in object space. And then I also have the position of the object. And those are two very different things. So let's take a look and let me explain exactly what's going on here. So position in object space means The data of the vertices are the pixels relative to the pivot of the object. But the position of the object itself means I'm not getting data for each pixel or for each vertex of the object. I'm getting data for the object itself. And the interesting thing about object data is that it's exactly the same for every pixel and every vertex on the whole object. Let's go ahead and plug this data into our base color and our emissive here just to take a look at what we get on the sphere in the scene. So here you can see that our object is completely black. And the reason that it's black is because it's placed right at the center, which means the values that it's getting are going to be 0, 0, 0. Now, as I move my object, you're going to see that it's going to turn blue as I move it in the Z direction. And it's going to turn red as I move it in the X direction. And it's going to turn green as I move it in the Y direction. And you can see that that color that it's receiving is uniform because we're passing in the position of the object for every vertex or every pixel that we're adding that data to. So it's not the position of each point on the sphere, it's the position of the whole sphere itself. And that's useful because, well, it's useful for the exact reason of the example that I'm about to show you. So let's come down here and we'll take a look at what we've got. So here is my object position. I'm passing it in and then multiplying it by 3. Then I split it up into its components. So I've got it split up into the R, G, and B, or the X position, the Y position, and the Z position. And what I'm doing here is I'm adding all 3 of them together. So first I add the red and the green together, then I add the blue together. So what this is going to give me is X plus Y plus Z. And then I'm taking the sine wave. Now in a couple of videos ago, we had a video where we talked about sine wave. If you want to take a look at that one, you can click on this link right here in the upper right. But I'm passing that into the sine wave, which is going to give me a waveform that's between the values of -1 and 1. But I want the values to be between 0 and 1. So I'm using the remap node and setting my in mapping to -1 to 1 and my out mapping to 0 to 1. Okay, so what is this going to give us exactly? Well, I'm going to go ahead and plug this into the emissive and to the base color of my master stack. And let's take a look at what we're going to get. So as I move my sphere around the scene, what you're going to see is, depending on the object's location in the scene, I'm now getting some value between 0 and 1. So I can move it over here and get black. I can move it over here and get white. And depending on where I place it, I'm getting some different value, right? So what can I do with this? Well, I can use it as a mask. So now, in my scene, I could use a lerp node, and I could pass this into the T socket of my lerp node, and now I could blend between 2 different colors or 2 different textures or whatever I wanted. So depending on where I place my object in the scene, it's going to get different values depending on its location. And that's going to allow me to make each instance of this object that I place look slightly different from the exact same instance that I place next to it or a little bit further away. And so I can use this technique to vary up the look of all of the instances of the same object. So even though those objects are the same model, the shader that I'm applying to them is going to look different depending on where in the scene I've placed it. So that's a really good technique to break up your scene and allow your environment artist to use the same model over and over, but have it look slightly different. And you can use lots of different techniques for varying it. Like I said, you could blend between 2 different textures with this, or you could blend between two different colors or two different smoothnesses. You can do all kinds of things. All right, let's take a look at one last example. And in this example, we're going to be using our position data to actually project textures onto our model. So here we have our position in object space. And again, we're using our swizzle node to just isolate the X and Y of the position. And then I'm passing that position XY into my texture sampler to sample a texture. So let's plug this into our master stack and take a look at our results. And I'm just going to move the master stack down here so that we can get a little bit better look at things. Okay, so now I've got my texture projected onto my model using the X and Y of my position. Well, let's take a look at what we get in our scene. So here is the flower vase texture, and you can see that as I move it around, this texture is kind of stuck to the surface, and you can see that it's projected along the Z-axis. Because I'm using the X and the Y of my position data, that means it's projected kind of in this direction here along the Z-axis. And you can see that if I look at it on the side here, the texture's kind of stretched and it looks kind of weird. But the texture does look good if I look at my sphere from this direction. You can also see that because the position is in object space, as I move my sphere around, it's staying put, it's stuck to the object itself. And as I rotate it, again, it's stuck to the object. But if I switch my position from object space to absolute world space, now you can see that it doesn't matter if I rotate my object, the projection is staying put in the world. And if I move the object around, the projection is also staying put in the world, but my model is moving through it. So I get this really interesting phenomenon where I've got this texture that's being projected that exists in the world, and my model is actually moving around through that texture. And so that's a really cool effect. This is a really nice way of projecting textures using just the world space position. Now let's say I wanted to project it from the top down. Let's try to do that. So I'm going to switch back to my shader, and if I want to project it from the top, I know that that's the y-axis, so I'm going to need to use the x and z values instead of the x and y. So let's save that. Now if we take a look at our scene from the top, you can see that now my texture is projected from the top. So I can change which of the three components I'm isolating to use as my texture coordinates, and it changes the direction of that texture projection. All right, so that's pretty cool. I've got three examples here. We took a look at creating a gradient that goes from the bottom to the top of your model using the position in object space. We took a look at varying up your model in the world using the object's position. And then we also took a look at projecting textures using the position in world space. Let's take a look at these three examples now in Unreal, and I'll show you how you can do the same thing in that engine. All right, so here we are in Unreal, and Unreal handles this data slightly differently than Unity. In order to bring in the world position, we have a node specifically dedicated for absolute world position data. In order to bring in the object position data, we have another node called local position. So instead of having one node and being able to choose which space you want the data in, we actually have two different nodes. And instead of calling it object space, they call it local space. And so I've got local position and absolute position. And just like in Unity, we can also bring in the object position. All right, let's take a look at the examples. So first, we're taking a look at the example where we shaded the model with a gradient from the bottom to the top. And that's very similar in Unreal. So I have my local position, and I mask out just the B channel. If you'll recall, Unity is Y up, and so I want to use the Y axis for my vertical gradient. But Unreal is Z up, and so I want to use the Z axis, or the blue channel here, for my vertical gradient. So I'm going to take my local position, grab the blue channel, and then the other difference between Unreal and Unity is that my units are in centimeters in Unreal instead of meters. So if I want my gradient to be approximately 1 meter, I'm going to multiply my centimeter value by 0.01, and that's going to give me the correct scale for my data. And then just like I did in Unity, I'm going to raise it to a power of 2, and I'll pass that into my base color. Now you can see here my position data. Here in the preview, the data is relative to the center of the sphere, but if I take a look at my test scene, now you can see that I've got my sphere with my vertical gradient going from the bottom all the way to the top. And also, one other thing that is a little bit different here is that the pivot point of my sphere, instead of being right in the center of the sphere, is at the bottom of the sphere. And so I don't actually have to adjust the data down. I can just leave it right where it is. And so that's kind of convenient. So there's my example of using the local position to create a gradient that goes from the bottom of my model up to the top. Okay, let's take a look at how we can create variation in the placement of our models. So for this, I'm going to be using the object space position, and I bring it in, and just like I did in Unity, I'm multiplying it by 3. Then I'm splitting the components, the red, green, and the blue, and adding them together. So I add X and Y, and then I add Z to the result. And then I take the sine wave of that value, and then I adjust the sine wave so that it's between 0 and 1. So let's pass this into our base color and take a look at the result. So now I have my sphere here in the scene, and as I move it around, you can see that depending on its position, it's going to have a different value. Now you might see that the frequency that it's changing at is really fast, and that's because of the difference between centimeters and meters between Unity and Unreal. And so in order to fix that, I would have to multiply my position just like I did here by 0.01, so that the position data is in meters instead of in centimeters. And now, as I move my object around, you can see that it gets a slightly different value depending on where I'm placing it in the world. Pretty cool. So I'm using object position, multiplying by 0.01, multiplying by 3, adding the components together, doing a sine wave, and then adjusting the results so they're between 0 and 1 instead of -1 and 1. All right, and for our last example, just like we did in Unity, we're going to take a look at texture projection. And this is kind of cool. In Unreal, you can see that my preview here is moving around as I move my graph window around. The texture is staying in the same position on the screen, which is a really good preview and an indication of exactly what's happening here. So I'm taking my absolute world position, putting it in meters, and then masking off X and Y. And let's take a look at what this looks like on my sphere in my scene. So here's my texture projected from the top, and because I'm using world space to move it around, the coordinates are staying fixed in the world, and my sphere is moving through them. So that's a pretty cool example. Now, you might be wondering, what if I want to project onto my object, but I don't want it to stretch? What if I want to limit the projection so that I'm only getting it projected on this axis and then it doesn't do this like ugly looking smearing? What if I want to project and mask this out so that it doesn't smear on the edges? Well, to do that, we need to create a direction-based mask. And that is the topic that we're going to cover next week. So be sure that you come back next week to see how to create direction-based masks so that when you do these world space projections, you don't get this smearing down the side. I hope you enjoyed today's video and that you've learned some useful ways to use position data, both for vertices, for pixels, and also for objects. Have a great week, everybody. Thanks for watching.